Good morning, everybody. First of all, I would like to thank the organizers for having invited me to give this review talk about the role of Alma in astrobiology. So I heard that this evening there is a wine and star session about Alma and music. Although I do love music and I'm a musician myself, I won't touch about that subject. So first of all, because I think it's a mixed audience, I will present very briefly what Alma is. Then I'm going to show what Alma can do in terms of essentially chemistry and also dust grains, and then show you examples from the diffuse interstellar medium up to protoplanetary disks about what Alma has brought in terms of our understanding of what I would call are the ingredients for astrobiology. It's like you go to the market for cooking, you know what the ingredients are, what the outcome of the cooking is. That Alma cannot answer yet. So Alma is an array of 66 antennas located in the north of Chile at high altitude at 5,000 meters, and to cover the entire accessible millimeter-centimeter wavelength up to 1 terahertz. The antennas are at 5,000 meters, and the idea is to be having moving antennas, so going from a compact to a very extended up to 16 kilometers, essentially mimicking a telescope of that size of 16 kilometers diameter. Everything is controlled remotely from a site that is below at 3,000 meters. So it's complex operations, and this is a picture I just want to show here. It's the only picture ever taken with an airplane of the Alma array. So Alma is probing in the electromagnetic spectrum, not the millimeter, centimeter wavelength region, which, contrary to the visible, essentially probes what I would call the cold universe. So you don't really see the stars, or you can, but essentially what you see is all the places where the stars are born and made, so the very obscured parts of our galaxy or external galaxies. So what is Alma measuring? It first of all measures the dust continuum, that are the dark clouds. It also measures, because most of the molecules do have their emission lines in that spectral region, so it is really one of the fields that created astrochemistry. And basically what you measure is a cloud of dust and gas, and I like this little cartoon. You can read the definition here, and you may perhaps also add something about life or astrobiology. So the Alma status, very briefly, I mean, the construction ended in 2014, and since then and today, Alma is in steady operations. That means that most of the antennas, the 66, are used for science operations day and night, and very successfully so. Also, as we speak, the observing modes are gradually increasing, and particularly I would like to mention here polarization, solar observations, also very large baseline interferometry, where you use Alma in combination with instruments in Hawaii, Mexico, and Europe. So things are pretty stable, are working very well, and I think you have seen, most of you, some of the outstanding results of Alma from the early universe to our solar system. So this is just a graph that shows you that the evolution from cycle to cycle, so essentially from year to year, from 2012 was 11 to today, and you see that in terms of the number of antenna offered, we are indeed in steady state. Each antenna is equipped with a number of receivers. Today there are 8 receivers, which are given here in red, and there are 2 more receivers that are, one being currently being developed and study, and the other one is in study, which is band 2. When all that will be done, then we will really cover with Alma the entire range from 35 gigahertz up to about 950 gigahertz in all the atmospheric windows. The recent band that has been added, and I would like to mention that here because I think it's relevant to this symposium, is the band 5 that covers the range from 163 to 211 gigahertz, so centered at 1.5 millimeter. The reason I mention this is that it's essentially being built to probe a line of water which is being observable from high altitudes, because the transition, as you see here, is possible. So you probe water directly, HDO and H218O, but also a whole series of other molecules. So this band has been offered for the current cycle, and I'm sure that results will come out from this, particularly on protoplanetary disks. So what is Alma contributing in astrochemistry biology? So first of all, there's a large frequency coverage, so you explore molecular complexity. You have a high spectral resolution, so you're limiting the line confusion and can identify hence the species. There's high sensitivity, so you can do unbiased surveys and probing near and far. You have a good calibration, so it's consistent relative line intensities, but is important for the identification. You have a high spatial resolution, so spatial coincidence of line and species and their distribution, which is new, and also the measurement of the continuum emission of dust grains, and particularly because you probe different frequencies, you have a probe of the grain size evolution in objects. So let me first start with the solar system. I will be very brief. Here is a sort of summary of all this topics that have been covered until recently. You see that basically all the bodies of the solar system have been studied, including the sun. But if you can look at the details, you see that also lots of chemistry has been done. I think that Alma is a fantastic support for even when there are missions going and visit the bodies of our solar system, simply because Alma is always available. It has a high sensitivity, and it also is very quick. So it's perfect for solar body type of observations. I'll give you one example here, which I think is very nice. It's in preparation, but it has to do with Io and the volcanism on Io. And here you see the detection of alkae, detection on Io here, KCl and NaCl, where you see the plummets of the volcanic activity. So that is one example where Alma can just do observation whenever something is happening, and then follow up and do deep observations in the chemistry. So let me give you a broad picture here about star formation and some of the things that Alma can do, because the audience is broad. So first of all, the formation of a star, here's a cartoon at time 0. You have a cloud of gas and dust, like in the cartoon, and then it evolves about in 3 mega years or so, a million years or so, into something that flattens, and so you form a disk out of which then later on planets will form, and eventually life will appear much later. So this is the broad cartoon of the formation of stars and planets. That takes the collapse takes about that time here. You have also the dust evolution, and from micro-sized grains up to millimeter, kilometer, and planets. And Alma is very good to probe the growth of grains from micro-size to millimeter. What happens in between the millimeter and the kilometer, I heard from a talk that was given last week, that this is a big question mark, essentially, that is not very well known, and it's an open question. So dust is very, very important, because on the surface of grains, which are essentially composed of carbonaceous material, carbon or silicates, you have a surface which is very cold, and upon which atoms can freeze and hence then interact and start chemistry, including very complex chemistry. And it's believed that in the interstellar medium and in starless cores, most of the chemistry is really happening on the surface of grains. I mean, they're the very complex chemistry, because it's simply very efficient, and the conditions, in particular the temperature, is very cold. So today, in the interstellar medium, from the gas phase, we know a lot of molecules. It's about 200, and here is I painfully wrote all this. It's based on the Cologne database of all the known molecules in the interstellar medium, with here on the top the number of atoms up to more than 12. Note that there are molecules, linear molecules like HC11N, but also like footballine or fullerenes of C60, C17, C60+. So it's very complex, and it's also, as you may have noted, there are organic molecules that have been discovered also in the diffuse interstellar medium. So the picture here, taken from a paper by Ehrenfreud, is showing you the sort of complex evolutionary cycle of interstellar organic matter. But note that in the interstellar medium, diffuse interstellar medium, you have fullerenes and pHs, which are sort of cyclic carbon molecules, complex ones, although the exact identification is not known. And they have a standing problem in the interstellar medium, which is still open, is the so-called diffuse interstellar bands that nobody has today been able to identify it, although it's known for more than about 70 years or so. It is supposed that it's due to very complex molecules, but what it is still remains a mystery. So organic molecules in the interstellar medium, there are many, Alma has contributed here to many interesting aspects. I would like to just mention here a paper by Arnaud Beloche, who will talk about it, I think, tomorrow, after tomorrow, in greater detail, which is the detection of an isomer of normal propyl cyanide, and in the direction of Sagittarius B2 in the center of our galaxy. And it's an isomer version that is about half as abundant as a normal form. And that's very important because, as you may know, branch molecules may be the rule rather than the exception in interstellar medium, but also, more importantly, it's a key characteristic of amino acids. There's also detection of aminoacetonitril, a potential precursor of glycine in the simplest amino acid, and cyanoacetylene, which is a contributor in models of prebiotic molecules in chemistry. All that was done with the 30 meter in Spain with IRAM, but I just mentioned that to illustrate the complexity of astrochemistry, even in a diffuse interstellar medium. Another way to probe the diffuse interstellar medium is to look at very strong continuum sources very far away that probe on their way to the Earth galaxies that are external to our galaxy. And then you probe an absorption, and you're very sensitive. I just mentioned that here because this is a very powerful tool to measure complete spectra and do the survey of what molecules are there. Today, with these techniques in this particular source, at a redshift of about 1, about more than 40 molecules have been detected, including species like argon H+. So this is a point, again, to illustrate the fact that the interstellar medium is complex, whatever the galaxy is, and that there are ways today, particularly with Alma, to probe external galaxies with very complex chemistry as well. So if you go to a starless core, out of which a star will form, many of the molecules are frozen on the dust grains, but of course you have also molecules in a gas phase. And this is a little cartoon that indicates, in fact, what type of molecules you can identify and measure depending on the depth or the amount of matter that is you are probing. And you see there's a whole variety here. And this is illustrated here with data which were not obtained by Alma, but I think they're very nice. It's a paper by Bergin and Tafada, where you see for dark starless core B68 the continuum, the dust grains, but then the different traces here in molecules, where you see that, in fact, they're tracing different parts of the starless core. But the bottom line here is that although the chemistry appears to be rich, it's not as rich as you think, because most of the complex molecules are frozen on the dust grains, and you can't see them in the gas. So this changes whenever the star is born, and then you have a very complex interaction between the radiation of the star and matter in the dust cloud, and so you can release part of the ice into gas and be able to, in fact, really probe the very complex molecules that were formed and are surviving the radiation in that type of cloud. And so this is a cartoon explaining this, but I won't enter too much in the details. So let me go into one particular case. So again, this is the same cartoon. So you have ice formed on the surface of the dust grains. It sublimates and injects molecules into the gas phase or enriching it. And then you have ice formed again when you go very close to the star. So it's very complex. So what molecules are formed as material is accreted to the circumstellar disk, and how? And how is the rich chemistry of the earlier protostellar stages incorporated into emerging planetary systems? So there again, you have the ingredients, you go to the market, you bring them, and somehow you cook them. The whole process and the details are still poorly known. So let me exemplify that with a recent series of measurements done with Alma on a source that is in Rho Fucus, which is a little dot here, which is very well known because it was an early source for detections of complex organics, including molecules like glycolaldehydes, or a type of sugar. So this is the image of the source, which is double, taken with Alma. This is a young star that is forming, and here is about the scale, which is 60 AU. So the PIL survey, which is not beer, but the protostellar interferometric line survey, is an unbiased Alma survey, which goes very deep, which is sensitivity that detects species with abundances about 1/100th relative to methanol. So 10 to the minus 11 to 10 to the minus 12 relative to molecular hydrogen. It is a survey done at 320 to 30 gigahertz. And so I will present you the results. So this is the result. That's the full spectral survey. You see it's full of lines. And the number of lines is about 10,000 separate lines and images for each of the lines, out of which about a few percent are from smaller non-organic molecules, about a third are known saturated organic molecules, and a third is isotopic variants of those organic molecules. So let me go very quickly into the complexity in this starless cores, where you just evaporate by the UV irradiation of the star the molecules formed on the ice grains. And you see that you have a startling amount of complexity. You have acetone, propanol, acetaldehyde, ethylene oxide, etc. So if you look at the abundances in the different regions here, you have glycolaldehyde, ethylene glycol, and you see that the ratios are very different from region to region. And of course, the question here is that either you have an early physical evolution of the sources, or you have initial ice composition, which is at play. Recently, there was a paper published based on these data where there was a discovery of CH3Cl, which was thought to be a biomarker, but interestingly enough here, and also limits on CH3F, but what's really interesting is the abundance of this molecule is comparable to what is found on the Rosetta comet, and I think we will hear more about that later this week. And so the detections reveal an efficient preplanetary formation of organohalogens, and it questions the whole concepts about how good a biomarker that is, and that these cometary impacts may deliver these species to young planets. So that's an interesting thing. But it's very clear that before its measurement, it was not foreseen that this molecule should have been detected in such a young star environment. So astrochemistry, biology with Alma and the interstellar medium, you have an interstellar space where essentially you have water and organics that is dominating. You have more than 200 molecules that are known, out of which you have a lot of organics and very complex organic molecules, such as amino acid nitrile, which is a precursor for glycine, amino acids, glycolaldehyde, a simple form of sugar, and cyanoacetylene. So let me now go to the protostars, where half of the carbon there is still in solid state in the grains, and the rest is mostly in carbon monoxide. You have a rich organic chemistry that is revealed as grain mantles evaporate into the gas phase. So you're probing part of the very complex chemical process on grain surfaces from early phases and during warm-up. You have a high level of deuterium fractionation, so I didn't really speak about that is found, which is important in the evaporated ices, and it's the fossil of cold phase formation. So in other words, you have hints of prebiotic chemistry in protostars, which may be the ingredients that you can bring into whatever planet you may form. So since I just mentioned the word planets, Alma has had a profound impact on our understanding of protoplanetary disks. This is a pre-Alma view of which was done with other instruments. It was a beautiful results at that time. But essentially what you see here with a few details are blobs. There are contours and blobs, and you don't see really any detailed structure. Those are the exact same sources seen a few years later in the continuum with Alma. So what you see here is a diversity of morphology from one source to the other, with gaps, rings, etc., even spiral arms. So you have a real zoology, in fact, of protoplanetary disks. And I remember particularly H.L. Tau, the first time I saw that, I couldn't believe it, because I thought that was a new model that would, be superseded with the Alma data. But no, it was Alma data, and the models had to be superseded. So how that all is linked with planet formation is still debatable, but I think there is a clear case, at least for H.L. Tau here, if you look at the models, that it's caused by planets that forming these gaps, and if so, they are lower than Jupiter masses. And you see here in the bottom that these are the model given here, and the model and the Alma data are very, very comparable. Another interesting result is W Hydra, which is seen here as the HST. It's a scale of 160 AU. Here's the diffused emission. And this is the image seen with Alma here, which I think is beautiful. You see again the rings, etc. This is done with long baselines. And this is the very center. So what you see here is the emission of the grains, tracing millimeter particle sizes. And if you look at the inner image here, you see that there is a dark annulus of about the size of 1 AU or so from the star that could possibly indicate interactions between the disk and young planets, and that needs further studies. So the disk structure that was shown by Nadir in his previous talk here, so I don't want to dwell too much here in the details, except to say that it is indeed very complicated and many things are happening. You have turbulent transport, but also you have a whole stratification in the disk between what is gas and what is frozen out into ice. And then you have the interaction of the radiation of the star, and all that plays a role. And so there's a whole process there of transformation of the ingredients that you put from the dark cloud into the protoplanetary disk that still requires a lot of study. So let me look now in the gas of the protoplanetary disks. First of all, one thing that I didn't mention is that in the terms of the distribution of the dust grains, another finding of Alma, I think, which is really interesting, is that there's a lot of examples of asymmetrical distribution of the dust grains, the millimeter dust grains. This is an example here. You see that you have more emission on one side than the other of the disk. And so that is supposed to, in fact, play a great role in the formation of planets. And you can think about these asymmetries in terms of the Kuiper belt object factory. So this is the gas in different objects, different tracers, CO, DCO+, HCN, C2H, etc. And you see that, again, there's a huge diversity, but Alma can do this. One of the interesting things about what Alma is doing is the definition and how to probe, in fact, the snow line, and particularly the CO snow line. And here you have examples of two sources where you see the CO snow line and then the detection of molecules like N2H+, that are probing those zones. There's also the detection of complicated molecules like the cyclic C3H2, which really probes the very inner parts of the disk, and with an intriguing structure with Keplerian rotation as well. And so C3H2 could become, in fact, a useful probe of radiation penetration inside the disks. Finally, the double DCO plus loops in MIM looping, so it's seen here, which is a direct consequence of the complicated chemistry when you go from the different zones, from the icy zones to the gas zones. And it's explained here. I don't want to go too much into the details, but indeed what Alma is able now to do is to probe these disks with high sensitivity and great detail so that you can really see what the different zones are in these disks. Finally, the detection of a methyl cyanide in the outer parts of a disk, MWC 480, which the interesting result that the abundance of that molecule is very similar to what you see in comets. So that clearly protoplanetary disks outside of our solar system have about the same sort of physical and chemical condition that the original solar nebula. And let me go to two summary slides. So first, a summary on the protostellar disks and what I would call the chemically habitable zones. So the first thing is, how do the ISM and comets organics form? They're formed through a gradual march towards complexity, although the full extent of the complexity in pre-stellar phase or comets is still unknown. So then the formation of the disk preserves this ISM materials, and there's a further evolution which is driven by the physics, but also the details of the planetary, let's say, architecture, the structure, and that inside a disk. And so it really depends on many things where everything is linked, as we heard in the previous talk. So what is the material that is supplied to forming habitable zones? Simple monomers can be made in ISM or in the disk and then supplied to planets. That is not known. But it's clearly Alma is providing essential data, as the gas provides information on the ice inside the snowline and also beyond the snowline. So concluding remarks and future prospects. First of all, I think that I have convinced you that Alma provided already basic information on the richness of the chemistry in protostellar cars, enabling detections of new complex organic molecules in the ISM and leading to groundbreaking results, dust and gas in protoplanetary disks. Ongoing and future observations include many things, including mapping of molecular gas emission in disk, probably now with water because the receiver is available, deeper spectral surveys, deeper than the PILS survey, to look for even more complex molecules, which need laboratory data to support it, surveys to trace evolutionary effects, so many hours spent on a type of objects, but also observing disks around protoplanets may be something that Alma can do in the future. Now, if you look down into the 10 of 20 next years, Alma should and will remain one of the main millimeter, submillimeter facility operating on Earth. And so into the many possibilities that have been discussed recently, it's to increase the sensitivity and the efficiency basically by increasing the throughput of the receivers, but also eventually by adding additional antennas to the baseline array. So with that, I thank you all, and Alma staff in particular, but also for your attention.